Hi everyone, my name is Niranjana Sankaran. Today I will be walking through my project on applying machine learning to solve the payer plan mapping problem in healthcare revenue cycle workflows. Here is the high level agenda and let's get to it. Let me start by introducing the problem. Healthcare organizations need to map payer and plan identifiers across multiple systems like electronic health records, clearinghouses, and payer systems. However, the same payer or plan often appears under different names, codes, or formats across systems. As a result, organizations rely on manual mapping and rule based crosswalks, which are time consuming, error prone, and difficult to scale. These mapping errors directly lead to failed eligibility checks and rejected claims, and increased manual work and other downstream impacts to business. Now, to evaluate whether this is a good ML opportunity, we look at three criteria. First, is there a real problem? Yes, this is a clear operational pain point involving repetitive manual work and inconsistent data. Second, can ML help? Yes. This is a classic entity resolution problem where ML can identify patterns across messy and ambiguous inputs. Third, does someone care? Absolutely. Mapping accuracy directly impacts transaction success rates, operational cost, and revenue outcomes. So, overall, this is a strong candidate for a machine learning solution. Now that we have established this is a good ML opportunity, let's walk through the business understanding using the CRISP DM framework. Problem definition. The core problem is that healthcare systems must map provider specific payer and plan identifiers to standardized IDs. But inconsistencies in naming and formats make this difficult. Target users impacted by this mapping are RCM operations team and automation workflows. Today, this is handled through manual mapping, rule based logic, and tribal knowledge among revenue cycle operators. And there are several gaps with this, including poor scalability, high maintenance cost, and no auditability of the mapping decisions, among others. Why this matters? Incorrect mappings lead to failed transactions, misrouted requests, and increased rework. This ultimately results in higher operational costs and delays in revenue realization. Now let's look at the success definition of this solution. Success for this would mean reducing manual mapping effort, improving transaction success rates, and increasing automation opportunities. We would measure this using the following business, also known as outcome metrics: reduction in manual effort, reduction in transaction failure rate due to mapping errors, reduction in rework or correction cycles leading to quicker time to collect cash, increase in successful automated mapping leading to potential automation opportunities for the RCM workflows. Please note that these are different from models performance metrics, also known as output metrics. Below are some of the model metrics we could use for measuring the model's performance. Top 1 accuracy, top n recall, how accurate are the ML predictions indicated by users' acceptance, and the confidence calibration. Some of the constraints that need to be considered here are the ability of the solution to integrate into existing workflows. Human review needs to be accounted for, especially the low confidence cases. Availability and accuracy of the data, it varies from provider to provider systems. That needs to be accounted for. And we should also take into account the latency requirements for the specific RCM workflow that we are trying to solve. Here are some of the relevant factors for the model: payer and plan attributes, external identifiers, text similarity signals. For instance, BCBS and Blue Cross Blue Shield mean the same. Contextual data patterns like historical data mapping patterns. I would like to call out that missing data attributes, outdated mapping due to the changing nature of the RCM ecosystems, and inconsistent data have the potential to impact the outcome and the output of the model. So, overall, I would say this is a well defined problem with measurable success metrics and rich data signals for machine learning. Now, let's talk about the solution and how we validate it. The solution uses machine learning to recommend the most likely payer plan mapping based on data similarity, historical outcomes of payer interactions. Instead of relying on fixed rules, the system generates a ranked list of candidate mapping, assigns confidence scores, and allow users to accept or override suggestions. The key idea here is the model learns not just what looks similar, but what has historically worked as well. Using historical real world pair interactions is a distinguishing solution aspect which is expected to increase the prediction and accuracy rates and confidence scores. Let's talk about the validation approach next. To validate the solution, we will follow an iterative process. Establish baseline performance using rule based approaches. Run offline experiments to validate improvement offered by ML in comparison with rule based mapping. Then we test with users using a prototype UI. We should also consider doing shadow deployment alongside the current system. Then conducting A/B testing to measure real business impact in a controlled live experiment. Last, but a very crucial aspect of continuously refining the model, iterate and refine. This ensures the solution is not only accurate but also improves real world workflows. Next, I'll briefly walk through the key design decisions here. Each decision is driven by user requirements, constraints, and the nature of the problem. Let's look at cloud versus edge. We chose a cloud based approach because it supports large data sets, which payer and plan is going to be. It enables centralized learning across provider systems, which more often than not, there are going to be payer plan mapping needed for multiple provider systems, and it does not have strict latency constraints. You are able to do the mapping upfront and utilize that mapping in your real time workflows. Based on these factors, we have chosen a cloud based approach. Next decision point is offline versus online learning. We use offline learning because payer data changes relatively slowly and it allows for safer, more controlled model updates. The next decision point is batch versus online prediction. We have chosen a hybrid architecture. The hybrid architecture will offer up the best of both worlds for this use case. Batch prediction can pre-compute common mapping and high confidence matches and store them as lookup tables or cache them. This will help save on compute time and cost and give us consistent results. Online layer will be effective for unmapped and ambiguous instances. ML model will run the prediction and surface it up to the users via a UI so that they can accept the prediction or they can recommend changes. So overall, the design balances scalability, reliability, and real-time usability. Next, let's look at potential risks in production. I would call out the key risks as training serving skew caused by differences between training and real-time data. Data drift caused by new payers, formats, or provider patterns or payer patterns. Concept drift caused by changes in what constitutes a correct mapping. A few additional risks would be feedback loops where the model reinforces its own errors, silent failures where incorrect mappings look valid. Then you should also take into account label quality issues from inconsistent human decisions. The risk type, what's causing the risk, and the potential impact are summarized here. To manage these risks, we should consider monitoring confidence scores over time to detect drift easily, and monitoring operator override rates as a proxy for model degradation. We should also implement shadow testing before deploying model updates, which would give us more control over the model changes and the outcome. Establishing retraining cadences tied to drift detection thresholds. Then we should do segment monitoring by provider, payer type, and geography to catch localized issues. Overall, machine learning presents a scalable and high impact solution for payer plan mapping, particularly when it is implemented with strong monitoring, feedback loops, and human oversight. Thank you for listening to my presentation. Have a great day.